and has good electrical and thermal conductivity.
Okay, so that's hard, shiny, malleable, which means it can be bent into a shape without breaking, fusible, which means it can be fused together, oftentimes by welding, and ductile, which means it can be put into a long wire.
It also has good electrical and thermal conductivity, which means it's great at transferring heat and electricity. Let's take a look at this at the molecular level, shall we?
In pure metals, the atoms are arranged in orderly rows and columns. Each atom gives up some of its electrons to create a kind of sea of these randomly moving charged particles. It's these free-flowing electrons that make metals conductive. When placed in a circuit, the negatively charged particles line up and flow as an electric current.
So that means if you hold one end of a long piece of metal and put the other end over heat, you'll eventually feel the heat on your hand where you're holding, even though it is not in the heat source. How cool is that?
Metals can be organized into different groups according to their physical and chemical properties. This can be clearly seen on the periodic table. Why don't I show you? That's better. First we're going to talk about alkali metals. Alkali metals are the 6 metals found in Group 1 of the periodic table. They include lithium, sodium, potassium, rubidium, cesium, and francium. These metals are all shiny and soft, and they could easily be cut with a knife, as you can see here as Kelsey cuts sodium. The metals in this group all have 1 electron in their outer shell, and are therefore very reactive. Watch as sodium is dropped into water. Its outer electron bonds with the OH in water, and hydrogen gas is released in an explosive manner. As you move down the alkali metal group, the metals get more and more reactive. Here is the reaction of potassium with water, which occurs even faster than that of sodium. Even more reactive still is the reaction of rubidium with water. And finally, cesium.
And it does.
Now we're going to talk about alkaline metals. Alkaline earth metals are softer than other metals and readily give up their 2 valence electrons to other substances. They have high melting and boiling points, but they tarnish quickly in air. These metals are used in many different aspects, from airplane hulls to racing bikes. Calcium is even found in teeth and bones.
Transition metals.
Transition metals are found in the center of the periodic table and are characterized with a partially full D shell of valence electrons. Transition metals are also known for their colors and are used in pigmentation for paints and dyes. For example, copper burns a lovely green, while cobalt is used as blue pigment.
Other metals.
Other metals have valence electrons only in their outer shell. They are solid, have a high density, and are opaque.
And metalloid.
Metalloids sit between metals and nonmetals on the periodic table, and they exhibit properties of both metals and nonmetals. They also act as semiconductors.
Silicon is the standard bearer of the semiconductors, materials that change from free-flowing conductors to non-flowing insulators when we simply zap them with an electric current.
Now you know all about metals, so what's an alloy? An alloy is a material composed of 2 or more metals, or a metal and a nonmetal.
Alloys improve the physical properties of a main metal, like making them stronger, more durable, improving the ability to conduct electricity, withstand heat, and even make them rust-proof. Here's an example when copper is added to tin.
Adding tin to copper during melting changes the properties of the metal. the larger tin atoms restrict the movement of the copper atoms, making the material harder. A blow causes the atoms to vibrate, but the tin prevents them from moving too far out of position.
In addition to their increased strength, alloys alter melting point. Brass, an alloy of copper and zinc, has a melting point of 900 degrees to 940 degrees Celsius, much higher than zinc alone. Even with our best efforts, we were not able to reach these high temperatures in our lab. Pure zinc melts at 419 degrees Celsius, much lower than its alloy with copper. Tin's melting point is even lower still, at 232 degrees Celsius.
Metals and alloys are also great conductors of electricity. In order to show this, we set up a simple circuit which, when complete, would light up a light bulb. The battery was 6 volts, which would have burnt out the light bulb, so a resistor was needed to control the voltage. The metal was the final component of the circuit, allowing electrons to pass through and conduct electricity. Because alloys change the properties of pure metals, they are often more useful. Pure metals are often softer and therefore bend and break more easily, like gold for instance. With the addition of alloys, metals can be more resilient. Alloys are found everywhere, in everything from dental fillings and jewelry to hinges and electrical plugs. They are used for airplanes and weapons, buildings, and wiring. The extra stability alloys provide resist destruction more easily and are very important for buildings to be structurally sound.